Good evening, everybody, and welcome. We've got a very, very interesting talk coming up with Professor Böttcher. Cosmic dust particles, neutrinos, and the new era of multi-messenger astronomy, all the latest cutting-edge info. So we look forward to your talk, and over to you, Markus.
Yes, thank you. Thank you very much. Indeed, what I'll talk about today is probably something that most people don't really think about when they think about astronomy, doing astronomy not with light, but with other messengers. But let me first back up a little bit and I believe repeat a bit what I've talked to you about the last time I talked, namely the aspect of multi-wavelength astronomy. So most of us are used to thinking of astronomy as just using the light that we see with our own eyes. So this is the night sky as we see it with our own eyes. We see primarily stars, essentially, because they are brightest in the kind of wavelengths that we see with our own eyes. But light is only part of the big electromagnetic spectrum. What we perceive with our eyes as different colors is in fact different wavelengths of light. So with short wavelengths or high frequencies representing blue light, and long wavelengths or low frequencies representing red light. But only because our eyes can't perceive longer or shorter wavelengths doesn't mean that the spectrum ends there. It goes way beyond the optical range towards longer and shorter wavelengths. And in particular, what we see at different wavelengths, at different frequencies, kind of represents the temperatures, the energies of things that we are probing with our observations. So at the longest wavelengths, we have radio waves, then infrared, then comes our visual optical light. Towards shorter wavelengths, we have ultraviolet, X-rays, and gamma rays. So in the radio range, we probe low energy radiation. If that corresponded to a temperature, it would be very cold, like less than 100 degrees Kelvin. The Kelvin scale, as you might know, is the absolute temperature scale, with absolute zero being 0 Kelvin, being minus 273 degrees Celsius, and then the same scale as Celsius, just starting from absolute zero. In the infrared, we probe things that actually correspond to temperatures of about 100 to 1,000 degrees Kelvin. Mostly what we see with infrared radiation is in fact dust that absorbs visible light, but that dust is irradiated by stars, heated up, and that dust radiates that energy back in infrared light. Our own bodies have temperatures about 300 Kelvin. That is why if you look at us with an infrared camera, we light up very brightly because we're smack in the middle of the temperature range where infrared radiation is emitted. In optical light, visible light, we see things that are a few thousand degrees hot, and that's primarily stars. And that is the reason why almost everything we see in the night sky is stars, because stars have just the right temperature to emit in the visible light that we can see with our own eyes. If we go to higher frequencies, we go to ultraviolet, where we probe things that are of the order of 10,000, even 100,000 degrees hot. It's still mostly stars that we see, just more massive, brighter stars than our sun. In X-rays, we probe things that are of the order of 1,000,000 degrees hot. And in gamma rays, we probe the most energetic things that are, if it was thermal, would be 10 million degrees and much higher energy than that, although the analogy with temperature kind of breaks down here. Now, why should we observe something in all these different wavelengths and not just use an optical telescope? We just illustrate that with a visible light image of the nearest active galaxy to us, that's Centaurus A. That's what it looks like if you look through a very powerful telescope in the light you see with your own eyes. So it's mostly the bright stars that make the white hue here, and you see that the central region of the galaxy is in fact hidden from us from dust that absorbs the visible light. Now we go to longer wavelengths. Remember what I said, the dust is heated up by the stars and re-radiates that in infrared. So if we look at that same galaxy in infrared radiation, we see kind of a negative image here. So where the visible light has been absorbed, we actually see the infrared radiation from the dust. And now we're looking at the exact same galaxy, the same orientation in radio waves. and that's what we see. It's the exact same thing, same orientation, only that here now we see something that looks like jets moving away from the galaxy in a totally different orientation than the galaxy itself. As in fact, jets, it's streams of gas that shoot out essentially perpendicular to the galaxy. A totally different image of the same galaxy just by using different wavelengths. So if we go from the visible light towards shorter wavelengths, we go to ultraviolet, where kind of we see the same picture, where ultraviolet light is also absorbed by that dust lane, and we see the bright hot stars. And X-rays, again, it looks totally different. You don't see much of the galaxy itself anymore. We see some kind of inflated bubbles of really hot gas that's millions of degrees hot gas that radiates in X-rays, but not really in the visible light or any other wavelength range. You also see these funny jets showing up again in the X-rays that we saw in the radio waves. And this is now the composite image where we see the visible light image in white here, and whatever is blue here, that hue, that is the extended gamma ray emission at the highest energies that we see from this galaxy. So the upshot being, to probe really everything that is going on in astrophysical objects, in most cases, you really need the complete multi-wavelength picture from radio waves all the way to gamma rays to really get all the information there is. But that's still not all we can do. But before I talk more specifically about neutrinos, let me just introduce an energy scale that is very useful to talk about energies of particles that are radiation, called photons. And on the same scale, we can then also post neutrinos. So the energy scale is called electron volt, the energy that an electron gains when it undergoes a voltage drop of 1 volt. And visible light actually has energies of just a few electron volts. So electron volts is the characteristic energy scale of light particles of visible light. When we talk about X-rays, X-rays are emitted by things that are about 1,000 times hotter. That means the radiation carries energy about 1,000 times more. We talk about kilo-electron volts or 1,000 electron volts in X-rays. And if we go another, 3 orders of magnitude, another factor 1,000 more, we're going to millions of electron volts, mega electron volt, MeV. That's the low energy end of gamma rays. So the energy scale of gamma rays, strictly speaking, doesn't really have an upper limit or so. It starts out at about 1 million times the energy of visible light, but we observe gamma rays also at high energies, at giga electron volt, 1 billion times the energy of visible light. And even with the Hess telescopes that I talked to you about last time, I think it was 2-3 years ago, we talk about tera electron volt, 1 trillion electron volt. So 1 with 12 zeros times the energy of visible light. So just to set a typical energy scale of energies from visible light all the way to the highest energy gamma rays. Now, where neutrinos can actually be useful is that light only emanates from the surfaces of objects that we see, like the surface of our sun. We can't see anything that's inside the photosphere of our sun. There's very dense centers of some galaxies that are completely hidden from us. There's the interiors of very compact objects like neutron stars that I'll talk a little bit more about later. And we can actually probe these with neutrinos. So in order to explain what neutrinos are, please indulge me for a little bit of background of nuclear particle physics. All matter that we see in the universe is made of elementary building blocks that are protons, neutrons, and electrons. That's gas, stars, dust. It's our sun, our planets, life on Earth. We all are made of these very basic building blocks, with protons and neutrons making atomic nuclei that are surrounded by electrons swirling around these atomic nuclei. Protons are heavy particles with a positive electric charge. Neutrons almost actually a little bit heavier than protons with 0 electric charge. Those make up the nuclei of all atoms in the universe. And then there's electrons about 2,000 times lighter than protons and neutrons. They swirl around, being held in orbit essentially by the attraction of positive and negative charges that make up the whole atom. So protons, neutrons, and electrons make up everything. So how do we determine what kind of atom this is that we have here? That's all just determined by the number of protons that are in this nucleus. Specifically, so the simplest ones we have, hydrogen is only just one proton that is swirled around by one electron, held together just by the electrostatic attraction. The next simplest atom is helium, has two protons. But now protons have the same charge. They don't like to get close to each other. They repel each other, right? Equal charges repel each other. So to keep them together, you actually need neutral particles to kind of glue them together. You can really imagine them as the glue that keeps the protons together in the nucleus so that it doesn't fly apart from its electrostatic repulsion. So in the helium nucleus, we have two protons, two neutrons, and then two electrons to swirl around to make it charge neutral. Then we have carbon is 6 protons and 6 neutrons, nitrogen 7, oxygen 8. And for these lighter elements, nature usually prefers that there's an equal number of protons and neutrons. Hydrogen really being the only exception, that you only need a proton, you don't need a neutron there. But for all the other lighter elements, you have the same number of protons and neutrons. But occasionally, nature produces nuclei that violate that rule, especially in kind of violent explosions like supernovae or so. Sometimes nature produces elements, nuclei, with too many protons or too many neutrons. One famous example that you might have heard of is called carbon-14, that one can use through its radioactive decay to date the age of dead material. It's called carbon-14 because there's 14 heavy particles in the nucleus. Remember, carbon is supposed to have 6 protons, 6 neutrons, so only 12 particles. But carbon-14, occasionally produced in such violent explosions, has 6 protons and 8 neutrons. And nature doesn't like that. So that's why this is in fact unstable, and it decays by converting one of those neutrons into a proton. Talk about 5,700 years for half of the material to decay this way. So the neutron turns into a proton and an electron, because we can't just produce a positive charge without having a negative charge to balance it. So we have the neutron turning into a proton and an electron. But what does that do? Instead of the 6 protons, we then have 7. That turns carbon into nitrogen, because 7 protons makes a nucleus, a nitrogen, a nucleus. So carbon decays into nitrogen with a half-life of about 5,700 years, and an electron comes out that's often termed beta radiation. So far, so good. But now there's something missing somehow. That was realized by Wolfgang Pauli already almost 100 years ago. Namely, the carbon nucleus and the nitrogen nucleus have very clearly defined energy states. So there's a difference in energy between the carbon and the nitrogen that the electron is supposed to take up. But Pauli realized that the electrons do not just have one energy, they have a broad distribution of energies. And energy is missing. Something else carries energy away there, and no detector picks it up. If there was another electron, a proton, a positron, or a gamma ray or something, detectors would have picked it up, but nothing was picked up. So there's an extra particle somewhere carrying away energy that's not picked up by any detector whatsoever. And that was first theorized and later directly detected. That is this mysterious particle we call a neutrino. There's no charge, because that would have been seen in the detector. It has no mass, but it carries away energy, and it interacts with essentially nothing. It goes through everything without doing anything. That's why no detector picked it up. This, in fact, also resolved a mystery of this decaying neutrino, because sometimes it happened that detectors saw a neutron decaying into positron and electron, and the positron and electron kind of going in the same direction. That can't be, right? If you're at rest on a moving car and you throw something in one direction, you push yourself in the opposite direction. So if there's no sense of motion to beginning, no momentum in the beginning, there must also be a balance of momentum in the end. So something else must have gone the other way to pick up that sense of motion, and that was that neutrino. So the neutron decays actually not only into proton and electron, but this funny neutrino comes out. Upshot being, this happens every time in some kind of nuclear interaction. A proton converts to a neutron, or a neutron converts to a proton. So this is what neutrinos are. We get them every time some nuclear reaction converts proton to neutron, or vice versa. So where does that happen in the universe? From where in the universe do we accept to see these kinds of neutrinos? Now, the biggest source anywhere near us is in fact the sun. So the sun makes its energy in a nutshell by using sort of 4 hydrogen nuclei, that's just protons, and converting them to helium, and that puts out a bit of energy. That goes through several steps. First of all, you need to get 2 hydrogen, 2 protons to get together, to slam together and react. Of course, the protons don't like each other. They repel each other. They have the same charge. So you need the protons to move very fast. Moving very fast means it must be very hot. That's why you don't see this happening everywhere in the universe all the time. You need the interiors of stars to exceed a temperature of about 10 million degrees. Only then can you get the protons close enough together that they can actually start making this fusion reaction. The center of our sun is about 15 million degrees, so that's enough. That's why the sun can do this. It can fuse hydrogen into helium. But once they react, in fact, the 2 protons alone don't like to stay together, but they can stay together by converting one of the protons to a neutron, ejecting an electron, a positron, to keep the positive charge, the antiparticle of the electron. And converting proton to neutron means you produce a neutrino. And for every reaction chain that converts to hydrogen into helium, this happens twice. Now, how often does the sun do that? I mean, the sun is pretty bright, putting out quite a lot of energy. And the energy coming out of one of these reactions is really just tiny, microscopical. The number of times the sun does this is, do not ask me how to pronounce this number. It's a 1 with 38 zeros. That's the number of times that the sun takes 4 protons and makes a helium nucleus out of it. That actually converts mass into energy. It burns away about 5 million tons of its own mass every second to make the energy that it radiates away. Now, 5 million tons, okay, the sun actually has 1 with 27 zeros of tons in mass, so 5 million tons really don't make a difference. But yeah, that's what's needed to sustain the energy output of the sun. And every time, every one of these 10 to the 38 times, it produces 2 neutrinos. So how many of those come here to us? I mean, lucky for us, the sun is 150 million kilometers away, so it's diluted well enough. But I don't know if anybody's online. Does anybody want to take a guess how many neutrinos are going through our bodies every second from the sun? And some certainly still make it through. But if anybody in the room or online would like to take a guess.
Shall we take a number and say 1,000 a second or something?
1,000 a second. That's a large number. All right. Well, the truth is, it's about 100 trillion.
Wow.
So 100 trillion, that's a 1 with 14 zeros. That's the number of neutrinos that go through our body every second of neutrinos from the sun. Now, doesn't really do much to us. That's a good thing. Neutrinos don't interact with anything. They go through everything, including our bodies. And I've survived it for over 58 years now. I'm pretty sure I will keep surviving it for another couple of years. But in fact, a colleague of mine from the University of Dortmund made a joke of it to put a sign on his office door saying, upon entering this office, your body will be penetrated by 100 trillion neutrinos per second, with the result that he's not getting his office cleaned anymore because the janitors refuse to enter. So one should be careful about the jokes one makes. But so that's what we get here. So now, how do we know this? How do we measure this? So first, back up. So I introduced the energy scale of electron volts. You remember, electron volts about energy of visible light. Gamma rays start out at about 1 million electron volts. This is in fact the typical energy that also these neutrinos carry away. In terms of, say, gamma rays, this is actually relatively low energy, but it's still 1 million times more energy than the energy carried by visible light. So that's where these neutrinos from nuclear interactions as they happen in the sun fit in. So now, as we said, they interact with almost nothing, but every once in a while they still do. It's only very rare. In physics, we say they have a very small cross-section to interact with anything. So to catch a reaction of these 100 trillion neutrinos per square meter every second, you need huge volumes of material that the neutrinos can interact with. And the biggest and most successful of these detectors for neutrinos from nuclear interactions is called Super Kamiokande, the Kamioka mine in Japan, not too far away from Tokyo. That's been fully operational since 1996. And you can see the dimensions of the tank that's filled with about 50,000 tons of water and surrounded by 13,000 photomultipliers that see light flashes from particles that are produced that when every once in a while a neutrino actually interacts with the material in the water and then ejects particles that can be detected. So this is what it looks like now filled with water. So one source of neutrinos apart from the sun that you see these neutrinos from the actions is the violent explosions of very massive stars that we call supernovae. So very massive star, like our sun, produces in the beginning energy from fusing hydrogen to helium. Later on, helium can be fused to heavier elements, carbon, oxygen, and it goes on and on and on. But at some point, that ceases. At some point, when you reach iron, you can no longer get energy out of making heavy elements. So once the core of the star is essentially all converted to iron, it can't produce energy anymore. The rest of the star still presses down with its gravity, and eventually the core just collapses, and the rest of the star explodes out. So this is what this was illustrating, that the star in its center exhausts its energy, the rest of the star explodes out, but the core collapses. So in the core itself, what happens then? Gravity becomes so extreme, if the star is massive enough, say more than 8 times the mass of our sun, gravity becomes so extreme that matter just loses its consistency of consisting of protons, neutrons, and electrons in atoms, where the electrons nicely have space to swirl around the nuclei. It's becoming so dense, so extremely squeezed that protons and neutrons are essentially forced, protons and electrons are essentially forced to converge to make neutrons. Now we're talking about the huge core of an entire star. That's a lot of protons and electrons that are converted to neutrons. So that means that gives a huge burst of neutrinos, with which essentially we see what's happening inside this extremely compact core that is called a neutron star. So these supernova explosions are probably the biggest source of nuclear neutrinos besides our sun. And the best example of that was in fact seen in 1987, called supernova 1987A, the first supernova seen in the year 1987 in the Large Magellanic Cloud. It was so bright that it was actually visible with the naked eye. You can see in the picture here on the left that the bright star here, that is in fact the supernova near its maximum of brightness after the explosion. And to the right, what it looks like right now, you can see the ring from material that has been shot out in the supernova explosion. So this is now almost 40 years later. And in fact, 3 different neutrino detectors, including Kamiokande, that's the predecessor of Super Kamiokande, and 2 other detectors, in fact, saw this burst of neutrinos, of mega-electron-volt energies. And interestingly, they saw that burst about 2 to 3 hours before the supernova was actually seen, because the neutrinos are produced when that core collapses, whereas it takes a while for the rest of the star to shoot out, form a shock, accelerate particles, and then actually make the radiation that we see as the supernova. So the neutrinos were actually kind of the warning signal 2-3 hours earlier to say a supernova is about to happen. Now, this is neutrinos of mega-electron-volt energies that are done in nuclear reactions, like in our sun. But neutrinos are also produced in other processes at much, much higher energies. For example, when protons interact with light or other kinds of electromagnetic radiation, they can produce lighter particles called pions that are unstable, that decay. When they decay, they make a neutrino, and another unstable particle, still a bit lighter, that's a muon, that is about 300 times heavier than an electron. The muon is also unstable, decays, and makes the antiparticle of the electron a positron. So a pion decays to muon and neutrino, muon decays to positron and 2 more neutrinos. So when you have these interactions of very energetic protons with light, you produce 3 neutrinos. But for that to happen, the proton has to have extremely high energies. And what I mean by extremely high energies, I'll put on that scale of energies in a little bit. But the system has to come up with the energy to make this pion, which is still a quite heavy particle. So the protons have to give that energy to these pions. And in the end, the neutrinos take up about 5% of the energy of the proton. So the neutrinos that come out are also much, much more energetic than the ones we get from the nuclear reactions. That can also happen by having 2 protons interact, turning one of the protons to a neutron and a charged pion, and then the decay chain is the same. So you produce a neutron and a charged pion, and the pion decays to muon and neutrino, and the muon again to positron and 2 neutrinos. So in this reaction, you also produce 3 neutrinos, and you also need extreme energies. To put the energies on this scale here, remember, so the highest energy gamma rays we see is now at the tera electron volt, and in fact, we have even seen gamma rays up to 10 to the 15 electron volts, so 1 to the 15 zeros. And that is in fact the energy where also these very high energy neutrinos come up. So they come at multiples of trillion electron volts to quadrillion, so that's the 1 with 15 zeros, times the energy of visible light. So literally on this chart, that they're literally off the chart. Yeah, that's the highest energies. Now, how are these detectors? The detectors like Super Kamiokande are not sensitive to these kind of neutrinos because they interact in a different way by actually kind of scattering on, say, electrons, or interacting and making extremely high energy muons that then also decay. What is happening when such a neutrino every once in a while actually does interact? It produces a whole shower of secondary particles that we can see through flashes of light. We call it Cherenkov light. And one can use, again, photomultipliers, photodetectors that essentially map where these showers are developing. So this is the way that one can detect these neutrinos indirectly. Of course, the fluxes of these neutrinos are relatively low and they almost never interact with anything. So in order to see one of them interacting every once in a while, one needs huge detectors, huge volumes of the order of a cubic kilometre. And the best one out there, the most successful out there, is at the South Pole, the Amundsen-Scott South Pole Station. That consists of 86 strings of these photodetectors, 1,000 meters deep and 1,450 meters below the surface of the ice of the Antarctic, and then going down another 1,000 meters. That has been fully operational since 2010. And now, because we have a bit of a problem that these kinds of tracks of things that make Cherenkov light are not only made by neutrinos from astronomical objects. The biggest problem is that our atmosphere is constantly bombarded by extremely high energy particles called cosmic rays. They have, in extreme cases, up to energies of a tennis ball hit by a professional tennis player in one single proton. So these particles, cosmic rays, interact with atoms in the atmosphere and make secondary particles, including these muons and neutrinos, as we would expect from astrophysical neutrinos. Now, somehow, we're astrophysicists, we're not interested in these cosmic rays, so somehow we need to throw away all these false tracks from these atmospheric muons and neutrinos. With the muons, that's relatively easy, because muons are charged particles that decay pretty fast. They don't make it very far. So if IceCube sees something actually coming from down below, something that came through the Earth all the way, it cannot be a muon made in the atmosphere. So this way, in order to throw out these muons made by cosmic ray interactions in the atmosphere, IceCube effectively looks from the South Pole through the Earth towards the northern sky. Because anything that makes its way all the way through the Earth can only be a neutrino, nothing else. But there's still a problem, because these interactions also make neutrinos. And there we can't really distinguish if that's a neutrino made in the atmosphere or if it's a neutrino made somewhere in outer space. So here, one has to look carefully at the energy of these neutrinos. So what's plotted here is the spectrum of neutrinos versus their energy. And in blue, you see this background of neutrinos produced in the atmosphere when cosmic rays slam into the atmosphere. That is relatively well understood, because one can measure the spectrum of the cosmic rays that come in, so one can relatively easily calculate what the spectrum of the neutrinos is. And since 2013, it's now established that beyond this very steep spectrum of neutrinos made in the atmosphere, there is a much flatter extension with a much harder spectrum, much more particles at very high energies, that's not made in the atmosphere, that must be made somewhere in outer space, that must be astrophysical. So the energy is about 100 tera-electron volt, so 1 with 14 zeros times the energy of visible light. Anything that has much more energy than this crossover is pretty certainly an astrophysical neutrino. So one of these neutrinos that, as multi-messenger astrophysicists, we're really interested in. We're not interested in what's made here in the atmosphere, because we're not interested in the cosmic rays. We want to know what's coming from outer space. So if we see neutrinos at much more than 100 tera-electron volt, the higher the energy, the more likely it is that it's actually coming from an astrophysical source. Even though, even at these very high energies, there's still a non-zero probability that it could still be made in the atmosphere, but just the higher the energy, the more likely it is that it's actually from some astronomical source. So this is an all-sky map of excess neutrinos that IceCube has seen. Of course, we want to know where in the universe is nature making these extremely high energy neutrinos. That also tells us where in the universe does nature accelerate protons to the necessary energy to make these neutrinos. And the most significant association that has been seen so far is with active galactic nuclei, the active centers of galaxies. So active galactic nuclei are the central regions of galaxies. We know that most likely all galaxies have a very massive black hole in the center. Our Milky Way has a black hole of about 4 million solar masses in its center. There's active galaxies that have even billions and more solar masses in the black hole in their center. Now, in most normal galaxies, like our Milky Way, there's not a lot of gas that can be accreted and swallowed by the black hole to make it shine very brightly. But in active galaxies, there is a lot of gas and dust that can be accreted onto this black hole. The gas heats up to millions of degrees, radiates bright in ultraviolet and X-rays, and in some cases, not only swallows material, but also shoots out jets of material that then dissipate their energy on extremely large scales, much larger than the scale of the galaxy itself. So this is a nice example here. We can see there's the active galaxy in here. There's jets shooting out, collimated streams of gas that shoot out with almost the speed of light, that are all powered by these central regions of these active galaxies. And we know now that a substantial fraction of the neutrinos that IceCube sees, in fact, comes from these active galactic nuclei. The brightest hotspot that IceCube sees, the brightest excess over atmospheric neutrinos, is in fact this Seyfert galaxy, a type of active galaxy. It's called NGC 1068, or the Squid galaxy. It's about 35 million light years away. And this is one of the brightest Seyfert-type active galaxies that we know in the sky. It's fueled by mass accretion into a black hole of about 8 million solar masses. And here, most likely, it is powered by this central accretion flow that drives winds into the surrounding environment and shocks the gas that protons can be accelerated and produce these neutrinos. But there's another kind of active galaxies that are also a very good candidate for producing these high-energy neutrinos. And in those, we have funny effects from these jets that I talked about, these collimated outflows that are streaming away from the central black hole. What we see here in this, that's actually a real radio astronomical imagery. So this is very high resolution radio images, a sequence over time. You can see here the years ticking away. And one sees individual blobs of material moving along these jets away from the black hole. The black hole itself is sitting somewhere here. And now we know how far away the source is. This is in fact a very well-known source. You see here the coordinates. It's better known as 3C273. In fact, the first quasar ever identified as such. If one just measures the speed with which stuff is moving away there, one measures speeds many times the speed of light, 10, 20 times the speed of light. Now, does that mean that relativity is wrong? Luckily not, because what is happening is that there is this jet, stuff is moving along the jet, emitting pulses of light or radio waves in our direction. We are sitting off here out to the right. But since this is moving with almost the speed of light at a very small angle with respect to our line of sight, the emitting region is essentially catching up with the light that it has just emitted. So by the time the light reaches us, the light particles are all bunched up in much, much shorter succession than they were actually emitted. So that gives us the impression of much faster motion than there actually is. And this gives us a direct estimate of the orientation of the jet and the speed. We know this must be moving with essentially the speed of light at a very small angle with respect to our line of sight to give us this superluminous motion. And that gives us, if there's speeds of almost 40 times the speed of light, that in fact tells us that the Lorentz factor of this relativistic motion must be of the order of 40 or so. So we know that there is stuff moving almost right at us with almost the speed of light. And that's in fact why we see bright emission from so many of them, because there's special relativity effects coming in, that all the emission is beamed in the forward direction of motion. It's all boosted in flux and in energy to higher energies. That's why these are in fact some of the brightest and most numerous gamma ray sources that we see in the sky. And it's now more and more established that probably 20% of the neutrinos that IceCube sees at these very high energies is likely produced by these blazars. That means these jet-dominated AGN with their jets pointing almost right at us. In fact, the most famous example of a direct association of a neutrino seen by IceCube and a blazar that was just in a flaring state. These blazars are variable in time. They're sometimes quiescent, and then they have bright outbursts of flux. And that's the most famous example, maybe the best association so far, was now with the IceCube event 170922. That's just the date, so that's 2017, September 22. An IceCube neutrino seen at about 290 tera electron volt. So that's like 3 with the 14 zeros times the energy of visible light, extremely high energy. So that's far above that threshold of about 100 TeV, where we can start being certain that it's actually from an astronomical source. And at the same time, the problem with neutrino astronomy is that it's very difficult to actually pinpoint where the neutrino really came from, because the tracks are not really very well pointing back to the direction of the source. So there's a relatively large error uncertainty of where it could have come from. But there's one so far really completely unknown blazar with this catalog number TXS0546. That was smack kind of in the middle of this error bar, and it was actually in a bright outburst, an exceptional outburst at the same time. And that gave astronomers big confidence that most likely that really is the source, because this blazar was just very active. You can show this here. This is the light curve. You can see years here. It's been monitored in high energy gamma rays by the Fermi Gamma Ray Space Telescope. You can see that it's never really done much. But here in 2017, right around the time of this neutrino detection, it went into this really bright outburst. This is going to zoom into the about 3 months around the time of the neutrino detection, indicated by the dashed red line here. So there's a bright outburst, beginning of a radio wave outburst. In optical, it was doing something. The unfortunate thing is that this was a very unremarkable blazar so far. But it is a gamma ray bright blazar, but the Fermi Gamma Ray Space Telescope has seen about 4,000 of them now. So it's nothing extraordinary. So nobody really cared about this source until September 2017. So nothing much was known about it at the time. But of course, since then, of course, it has been monitored more and more. But it's this coincidence that many mark the real beginning of multi-messenger astronomy. So the first time that we actually see the source not only in electromagnetic radiation from radio all the way to gamma rays, but also in a different messenger that is this neutrino. Of course, we've seen solar and supernova neutrinos before, but it's the first time that we have this kind of really confident association of this very high energy neutrino with a gamma ray outburst of the same source. So where is this going? The future, I think, is KM3net, at least one of the next big up-and-coming observatories. KM3net, standing for Kilometer Cubed Neutrino Telescope. It's the next generation neutrino observatory that's being under construction right now in the Mediterranean Sea with 2 subarrays. There's a smaller array off the coast of Marseille here. Oh, Toulon actually is the nearest bigger town. That's called ORCA, Oscillation Research with Cosmics in the Abyss, that will focus on fundamental neutrino physics. And for astrophysicists, more interesting is the bigger of the 2 arrays called ARCA, Astrophysics Research with Cosmics in the Abyss. This is the one that will actually instrument about 1 cubic kilometer of Mediterranean seawater with detectors. The detectors are these digital optical modules that you can see here on the ship, of one of them before it was let down into the Mediterranean. This is just an artist's conception of what it will look like. So these strings of these detectors are anchored at the bottom of the Mediterranean Sea, and then there's buoys that keep these strings straight upright. It's complete, currently about 30% complete, and we expect it to be about a factor 10 more sensitive than IceCube is right now. So it should be a huge boost to neutrino astrophysics. And in South Africa, we're in fact quite actively involved in this project with members at Northwest University, WITS, and the University of Johannesburg. Thank you.
Okay, can I file? Would somebody else like to? Okay, go ahead with your question. I'll just repeat it for the mic.
I'd like to thank this presenter, very clear presentation for what is actually a very complex subject. What interests me is that you look at the IceCube neutrino detector, and you look at the one in Japan, I can't even pronounce that word, and you look at that last detector that he's got, which is like a ball, which is possibly maybe 3 or 4 meters, maybe 6 meters maximum in diameter. How is it possible for the small ball to be more precise and detailed than those large detectors that they've got situated?
Yeah, but if you look at the image, sorry. So the question is, how could that, what looks like a small ball, be more sensitive? So I think you've got strings of those balls in a vertical column, and a whole lot of those columns, and that forms. So you've got how many of these balls would you have, Professor, in the cubic kilometer or seawater?
Indeed, right. This is only one of these detector units, and there is, don't get me wrong, I think there's about 230 of these strings, and there's 33 of these little detector units in each string. Right? So there's thousands of these little balls there in this whole detector volume of about a cubic kilometer.
So the volume of water which holds all those balls is actually the whole detector.
Yes, right. Because the water is the actual detector in a sense with which the neutrinos interact, and that produces light flashes that these detector units then see. But the detector is in fact just about the same size as IceCube, about a cubic kilometer.
Okay, I'm going to think of some of the questions I had. You spoke of multiple ways that neutrinos are produced. Have they got a small mass? Have we got any idea of what the mass is? And when they travel, the high speed ones, which comes from high energy ones, which come from space, which you're sure come from space, or relatively sure. Do they travel anything close to the speed of light, or just a fraction of the speed of light? Is there any idea of the actual speed that they travel?
They move with essentially the speed of light. Up until a couple of years ago, or maybe a decade or two ago, it was thought that they were actually massless, but we know they have a very, very small mass, much, much less than, say, for example, an electron or so. But we know they have mass because they're actually converting from one neutrino type into another one. I briefly mentioned that there's electron neutrinos and muon neutrinos. There's also tau neutrinos. There's 3 different types of neutrinos. And as they propagate from an astrophysical source to us, they actually convert from one type to the other. That is only possible if they actually have a non-zero mass. So we know they have a very small mass on the electron volt scale, probably of the order milli-electron volts. So very, very small. and they move with essentially the speed of light, but just because they have mass, they cannot move with exactly the speed of light, but very, very close to the speed of light.
Okay. And anybody else? Another question?
Assuming that the neutrinos come from one source for a particular event, they then travel in a straight line through space. They then hit the one side of Earth and all the humans on that side as well. They then go through the Earth and carry on. So basically, that stream of neutrinos actually goes in a straight line from the source and into deep space. Is that correct?
Correct.
Yes, right. Neutrinos are not deflected by anything. That's not like protons, so that are deflected by magnetic fields. Neutrinos, really, as you say, go just straight and through everything until every once in a while they do interact, but very, very rarely.
So they must radiate spherically away from the source. So I presume they also reduce the sort of density with the square of the distance from the source. Is that right?
Yes, same. Yeah, same as any other radiation.
Yes. Okay. So is there any way of detecting the sort of density? Does that give you any idea of the distance from the source or not? Is that too vague?
Yes, one can. One can, of course, measure fluxes, especially at the lower energies where the fluxes are somewhat higher. One can really measure fluxes, and that gives you essentially the densities of the neutrino stream that comes out. And for the sun, we know it pretty precisely. We measure that flux pretty precisely.
Okay, so I think you mentioned that, I can't remember who the person was that worked out there's something missing in the equation in the decay of a neutron to a proton, and then eventually discovered that it was a neutrino. And I think you also mentioned that when you have fusion of a very high mass star, the electrons fuse with protons into neutrons, and that also produces neutrons, which it seems like, I mean, neutrinos. It seems like the opposite of the other one, where neutrino is formed from a neutron decaying into a proton and neutrino. It seems the opposite. I mean, how was that worked out?
It can happen both ways, but that was the supernova explosion. That was the collapse of a star. Right? As you say, usually neutrons like more to decay into proton and electron, but in a neutron star, the gravity is so extreme, the pressure is so extreme that essentially the reaction is being reversed. So proton and neutron fuse essentially to become neutrons. Proton and electrons fuse to become neutrons, just because the pressure is so high that protons and electrons can no longer coexist separately. So essentially they're squeezed together to neutrons.
We have a question from, from a participant. Is it David Clark Brown? Would you like to speak?
Yes, thank you. It's really another fascinating lecture, and I learned quite a lot about the structure of the atom too, changing protons to neutrons. But I hope 3 quick ones. Can you tell which direction these things come in? And when you represent that energy in a wave form, it goes up and down, up and down. Would this travel, how would you depict energy otherwise than going, with your graph going up and down in a wave, a sine wave? And another one is the formula E equals mc squared. Is that the speed of light squared? So it multiplies itself? Yeah, thanks.
Yes. So yes, E equals mc squared really means mass is converted to energy. It's mass times the speed of light squared. And in fact, so that's how the 4 fusion protons to helium, the 4 protons are actually a little bit heavier than the helium nucleus in the end. And that is the difference in mass that is converted effectively to energy. And it's in fact, there's 5 million suns. Yeah.
Why is it the speed of light squared?
That would need some introduction to special relativity that I can't really do now in a few minutes.
I think you'll blow my you'll blow my computer. Thanks. Yeah.
Yes, right. And so the direction in which the conversion happens, it's really depending on what is more. In the carbon-14 example, we had too many neutrons, then the neutron decays into a proton. But there can also be nuclei where you have too many protons, and then to establish the equilibrium that nature likes, a proton can be converted to a neutron. Right? So it can really happen both ways, depending on which species is superior, or is too many, so to say.
Okay,
no, sorry, I was talking about the detector, whether you can detect which direction these things are going.
One can certainly in a detector distinguish whether there's an electron or the antiparticle coming out, as usually the detectors trace these secondary particles, and if there's a magnetic field, then the proton will be deflected one way, the electron the other way. This way, in fact, one could also distinguish between those.
So yes, yes is the short answer. Wim, did you have a question?
Yes, I have a question. At first, thanks for the invitation, and it was very interesting. But I wonder, the energies are very high. Is there also a possibility that gravitational waves occur at these occasions?
Depends on which occasions you mean. Of course, gravitational waves are being detected now since about a decade.
Yes.
And supernovae, if they are in anisotropic, so not exactly balanced, they can actually also produce gravitational waves. Active galaxies, not by themselves, but there's a suspicion that many active galaxies are actually also associated with two supermassive black holes, in fact, orbiting each other. That will produce gravitational waves, in fact, at very low frequencies that LIGO, Virgo, Kagra cannot see, but space-based antennas like LISA might be. So this is the way that also gravitational waves can come into play. It's mostly two compact objects merging.
Go ahead, Elaine.
How neutrino and the new one in different masses. And if I heard correctly, he was saying that they interchange. It changes from a tau to a muon to a normal neutrino. And I was wondering if different masses, there must be energies involved. Where does it come from?
Sorry, so Elaine is asking the question, where do the energies come from when one kind of neutrino converts to another one? And do different neutrinos have different masses, I think?
Yes, the neutrinos have different masses, and it's actually one of the open questions that Orca is trying to address of what actually the ordering of the masses is, which one has most, which one has least mass. And the energy can really just come from essentially kinetic energy, or then so there's it's the same that we just said, E equals mc squared. So energy can be converted versus mass and
Okay, sorry, did you have another question?
Yeah. The issue is, if these new neutrino sensors are so sensitive, are they able to monitor any activity at the Large Hadron Collider in Switzerland? In other words, if a neutrino is formed there, can that neutrino be picked up by these detectors or not?
Can the detectors pick up neutrinos sourced from the large LHC? And in fact, what about nuclear power stations and so on, which produce neutrinos?
There are experiments that actually do precisely that are essentially in the beam of neutrinos produced by, say, nuclear power stations or accelerators. I do not think that ORCA is set up to do that. ORCA will primarily work with atmospheric neutrinos, but there are experiments that do that indeed.
So, sort of, yes. Can we go back to sort of a little bit of nuclear physics that I remember? There's a thing called a quark, and a proton is made up of two of one and one of the other, and a neutron is opposite. It's, I don't know, one is two ups and one down, the other one's two downs and one up. So when a neutron converts to a proton, then the quarks are also converting, is that right? Or what is happening there?
Yes, in fact,
and how big is a quark relative to a neutrino? Is a neutrino much smaller than a quark even? Or what does a quark not have size?
But they're essentially all point particles, right? It's not really, can't really pinpoint a size. But indeed, what it comes down more fundamentally on the quark scale is that one up is converted to a down, and vice versa, when you convert a proton to a neutron. Yeah.
So if you say a proton decays, for example, a neutron decays to a proton plus a neutrino plus, I don't know if there's some energy as well. So the difference between that and the two up quarks and down quark and two down quarks and one up quark is also equal to the mass of a neutrino?
And there's also charge coming out, because up and down.
Okay. So there's energy involved as well.
Yes. So the mass difference essentially is the energy that the neutrinos and the electron pick up. But it's not purely the mass difference, because the electron and the neutrino will carry away momentum. So there's also kinetic energy involved there.
So in the equations, when scientists work these things out, they don't compare quarks and neutrinos and try to work things out that, or try to deduce anything about quarks from a neutrino or about neutrinos from quarks or anything like that. It's too vague, is it? There's too many parameters in it all.
No, I don't think one learns much about the structure of quarks from this. It's really more about learning the fundamental properties of neutrinos. But yeah, indeed, I mean, there is always an energy difference, and this is why it was so surprising that the electrons had this broad energy distribution. There is excess energy that is carried away by the electron and the neutrino. In terms of kinetic energy, it's not only the mass difference. Right?
All right. Anybody else? The questions are not ending tonight.
It strikes me that over the extended period of the sea where these things are installed, they pose a navigational hazard.
They're very deep. They're very deep.
So has he picked up any sort of problems with the subs knocking the wires and actually buggering everything up?
Yeah, how do these things, what happens with sea traffic or even whales and stuff swimming around these things? How does that affect them?
In fact, these detectors are partially also used for biological research. Say, for example, bioluminescence, because these detectors also pick up bioluminescence, light coming from animals, actually. We're very far down in the ocean, so essentially no sunlight comes down there. It's 1,500, I think, or 2,500 meters deep. So it is very deep. There's very little life left there. I don't think whales are actually getting this far down. But yeah, there's interference from life that needs to be taken into account and accounted for. Another problem also with being in the water, we're not rigid like an ice cube where it's all frozen in. There's sea currents. That means the detectors are not always exactly at the same place. But to essentially image the showers produced, one needs to know exactly where the detector is. That's certainly complicates things. And that's sort of, you're pinpointing exactly a problem there. It's not as steady and as stable as a detector in ice is. So one has to go through great lengths to account for that and to correct for that.
Very complex. There was a question at the back there. Nick?
Reducing the 96% of unknown energy. We say we only know about 4% of whence energy comes. Is it reducing that number of 96% unknown?
So the question is essentially about dark energy. Does the neutrino and its energy and the energy involved in the process explain any of the dark energy, or is that just totally separate?
Dark energy is certainly not. But dark energy is something that, in fact, pushes space apart. Neutrinos would not do anything like that. But there have been ideas that neutrinos could account for part of dark matter, in fact.
Yes.
But most likely the masses are just too small to make a substantial contribution.
So dark matter is also not really in the picture for neutrinos. Okay, very interesting questions we're getting tonight. We're learning a lot. Any more from the online participants? Any more questions? I don't see any more hands up there. And from the audience, no more? Have we run out of questions? All right, thank you very, very much for a fascinating lecture. And you can judge, I think, by all the questions that we're probably going to, it's a good thing I'm recording this, and we're probably going to have to go and watch it 10 times over, and we've probably still only taken a fraction of what you were talking about. But thank you very much. It's very, very, very good.
Yeah. Thanks for having me.
And we hope to see you in the future when all these things are working sometime. All right.
Yeah, glad to do this again.
Just one last quick question. The involvement of South African scientists in these various things around the world, is there some direct participation in the science being done by South Africans, people from South Africa?
Yes, certainly. I mean, we are involved, especially in the astrophysics working groups here. So KM3, that is only one thing we are involved in, but yes.
Okay, fantastic. All right. Thank you very much. Enjoy the rest of your evening.
All right. Yeah.
Okay.
Yeah. Okay. Bye.
Thanks everybody for the online participation.